Alright. We're going to be learning about three things. Diffraction. That's going to be the lighter, more complicated thing. Reflection. That'd be the middle thing. And the first thing is the Doppler effect. Have you heard of the Doppler effect? So we have the Doppler effect. Have you ever watched The Big Bang Theory? This is like the best quote ever. And it's like it's just Sheldon stating the definition verbatim. Come on.
Make a different future. Start different at GoDaddy.com.
I want to talk to you about before we go to the party.
I don't care if anybody gets it. I'm going as the Doppler effect.
No, it's not.
If I have to, I can demonstrate. So what time does the costume parade start?
The parade?
Yeah, so the
Where
judges
is it?
can give out the prizes for best costume. You know, most frightening,
This
most
does, like,
authentic,
all of them.
most accurate visualization of a scientific principle.
Oh, Sheldon, I'm sorry, but there aren't going to be any parades or judges or prizes.
This party is just going to suck.
Oh, come on, it's going to be fun. Yeah, now the Doppler effect. All right, I got a shower.
Where?
See?
Hi. Train?
Club.
I'll get it.
Let me find. It's just one line that I'm looking for. Doppler effect. Should only be like 10-second video. Actually, we'll do this. This should have it.
The Doppler Effect. In Sheldon's words,
It's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
There you go. You got that? I'll play it again.
Apparent change in the frequency.
in Sheldon's words,
It's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
So, Doppler effect. It's the relative change in apparent frequency It's the relative change in the apparent frequency due to the relative motion between the source and the observer. Let's see how close I got.
in Sheldon's words,
It's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
Source of the wave and that's
the Doppler effect is perhaps best explained visually. So here's a thing that is emitting waves. It could be a fire truck emitting sound, it could be a star emitting light, it could be a duck creating ripples on a pond. Those are all waves, and they all look something like this. We see the Doppler effect happening when the thing that is emitting waves moves.
So remember, a wave has crest, it has crests and troughs, and how you perceive the wave is basically how many crests hit you, or how many troughs hit you, and how many hits you per second is the frequency. You can work out velocity of the wave and time, and you can get distance, the wavelengths. Basically, though, if something is moving towards you, those incoming waves are going to hit you faster because it's moving towards you. Like for, well, you'll see it here when it starts moving.
It's In the direction it's moving, the wave.
So as it moves towards you, you see them starting to bunch up. And behind it, you see them getting away. So an object is moving towards you, the crests are going to get closer and closer together. They're going to start hitting you more faster and faster. So the wavelength decreases and the frequency increases.
Fronts bunch up, and behind it they spread out. If our object is moving towards a stationary observer, these bunched up waves are observed at a high frequency, and if the object is moving away from a stationary observer, the waves are observed at a lower frequency. So that is the Doppler effect, the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer. It makes sense, but it gets interesting when you consider some of its applications. So let's say you are standing in the middle of a road. That's you, and a car drives past you.
How does a car horn sound? Does it sound like it's two tones?
Very fast. As it does so, it honks its horn, because you're standing in the middle of the road. The horn to you might sound something like this.
Did you hear it? Dun dun. That's not what it sounds like. The change in frequency is you hear it first coming towards you, and then as it's continually honking the sound, as it moves past you, the frequency immediately changes. So you hear the switch. You hear a change in frequency.
So it starts at a high pitch and moves to a lower pitch, even though from the driver's perspective, the horn is playing the same pitch the entire time. So what's going on? As the vehicle's coming towards you, the sound waves that it's emitting bunch up, and so are delivered to you at a higher frequency, which you interpret as a higher pitch, because the frequency of sound waves is pitch. And then when the vehicle passes you and is moving away from you, the sound waves spread out, and so you hear them at a lower frequency, a lower pitch. So that's how the Doppler effect works with sound. It also affects another kind of wave, light. So let's say you look out your observatory and you see a star. Just like the car's sound waves, if the star is moving towards you, even just a little bit, the light waves that it emits will be bunched up, meaning that you see the light at a higher frequency than it actually is. Frequency in sound is pitch, so what does it mean for light? Well, if we look at our handy pocket electromagnetic spectrum chart, we'll see that a small change in frequency for visible light will change its color. Higher frequency light waves means bluer light, and lower frequency light waves means redder light. This is called redshift, and it may possibly be among the weirdest and coolest things of all time. Stars, or anything that you can see, change color depending on their relative motion to you. Of course, you can't see this minute difference with your eyes, but astronomers with the right equipment can use this effect to tell whether stars are moving away from or towards Earth. As it turns out, almost everything we can see in the universe is moving away from us very quickly, which is both an important piece of evidence for the Big Bang and an indication that the Earth might get very lonely in the distant future.
So as objects move away, their light actually gets more redshifted, meaning they lose frequency. Because as it's moving away, the crests are being emitted longer and longer and longer. So is energy conserved? I think in this class I've stated there are 4 things in the universe that are always conserved, no matter what.
Energy, momentum,
Linear momentum. Angular momentum. And coming up after the wave unit, charge. Is energy actually conserved in the universe? Can it be created or destroyed? Are you sure? How?
as you said, it can't be created.
It can't. So can it be created or destroyed? Are you sure? So what is the energy of a wave? An electromagnetic wave.
The energy,
Mm-hmm. This is one of the last things that was on the test. Energy of an electromagnetic wave is equal to Planck's constant times frequency.
Oh, yeah.
Now, whenever an object's moving far enough away from us, the light emitted in front of it's going to have higher energy. The light emitted behind it's going to have lower energy. So this balances out. Energy is conserved overall. But one thing we've learned is that the universe is expanding. The actual space between two objects is stretching out. So we have a light wave, and the fundamental space between each crest is expanding. What happens to the frequency of the wave? It gets shorter. Oh, yeah, the frequency, yeah, it reduces, yes. The wavelength gets longer. So frequency goes down. What does that mean about energy? Where did the energy go? Can it be created or destroyed? Then where does it go? Extremely advanced physics tells us that energy is only conserved if time is conserved. It's called time symmetry. Remember how I tell you that there's no direction in time? The only theory in all physics that tells us that time is forward is thermodynamics. However, we'll learn about this later on. The 3 dimensions we're used to, up, down, left, right, forward, backward, is actually a 4th dimension, time, forward and backwards in time. We actually live in space-time. Here's an interesting thing. Why do we have gravity? Why do we fall down? It's because time is space-time is curved. More specifically, it's the curvature in time. Your head is running at a faster clock rate than your feet. Your feet is moving ever so slightly slower. And this creates a net pull-down curvature. It's again extremely advanced. But if space-time is stretching out, time is no longer symmetrical. And energy isn't conserved whenever time isn't symmetrical. Theoretically, you break a glass, you throw a baseball, physics works the same way backwards. But if the actual universe is expanding, time isn't symmetrical anymore, and energy can be lost. It's extremely advanced physics, but it's an interesting fact nonetheless. So, the Doppler effect. Note that I'm going to reuse a symbol. Do not get it confused. C plus VR divided by C minus Vs times F naught. C is the velocity of the waves in the medium. And it's usually constant. Give you an example, the speed of sound, which is roughly 343 meters per second in normal atmospheric conditions. VR is the velocity of the receiver relative to the medium. It's positive if the receiver is moving toward the source. Vs is the velocity of the source relative to the medium. Well, I mean relative to the medium, I mean a stationary, non-moving thing, something you would call non-moving. It is positive if the source is moving toward the receiver. I always want to flip the I and E receiver. F naught is the original emitted frequency, meaning the frequency if nobody was moving. And F is the observed frequency. It's what you hear, what the observer hears. So to draw a nice picture, we have a source as emitting sound and moving in this direction. We have a receiver, you listening, moving in this direction. These values will be positive if they're moving in the same direction, or moving toward each other. And the frequency that we hear is based on this formula. Hear a change? So whether or not something's moving towards you or away from you, you can actually tell based on So these are standard frequencies. Every country has a standard frequency for a fire truck and an ambulance. If you have their base frequency memorized when you're just sitting still, you can actually, just by hearing, telling if the ambulance is moving towards you or away from you. Hear cars going by. So when it's moving away from you, you hear lower pitched sounds. And when it's coming towards you, you hear very high pitched. So let's do an example. So the speed of sound is 343 meters per second. at 20 degrees, I believe, Celsius at 1 atmosphere. Sea level at room temperature, basically. So our C value is 343 meters per second. Let's suppose, let me actually Google what is the frequency of an ambulance in the United States. They use a sweeping pattern between 500 and 1500. So we'll say that, let's say that the original frequency is 1 kilohertz. And let's say it's moving towards you at 60 miles an hour, 60 miles per hour to meters per second. Do some rounding. Let's say it's going, let me switch these. Say it's moving 30 meters per second. So the source is moving at 30 meters per second, which is roughly 67.1 miles per hour. And let's say that you are standing still, you're parked at a red light. So you are the receiver, you're not moving. So we have an ambulance moving towards you at 30 meters per second, emitting a sound at 1000 hertz. Question is, what do you hear? So our new frequency that you'll hear is equal to C plus VR divided by C minus Vs times the initial frequency. Since you're not moving, we can remove that. Is equal to C divided by C minus Vs. So this would be 343 meters per second divided by 343 meters per second minus 30 meters per second times 1000 hertz. All the meters per second get canceled. So if it's moving toward us, we would expect that the frequency would increase as the waves are bunching up as it comes towards you. And we see that it has a pitch of about 1095.85 hertz. So it's increased by almost 100 hertz. And it makes no difference whether or not the ambulance is moving at 30 meters per second towards you, or you're moving 30 meters per second toward it. It's all relative. Here's a algebra problem for you. Suppose a stationary alarm is blasting at 1000 hertz. you are moving and hear the frequency at 500 hertz. How fast are you moving? So we know the initial frequency, the stationary frequency, is 1,000 hertz. The new frequency is 500 hertz. We know that the source velocity is 0 meters per second. We know the speed of sound is 343 meters per second. And we're trying to find VR. So, F equals C plus VR divided by C minus Vs times F naught. To solve for VR, we can immediately roll out Vs, but I'm going to keep it in. I'm going to first divide by F naught, moving this to the other side. And I'm going to multiply by the denominator, C minus Vs. And that leaves me with C plus VR here. And then I will subtract the speed of sound, or the speed of the medium. F divided by F naught times C minus Vs minus C is equal to VR. Since Vs is 0, it's not moving, we know that thus the receiver sound, velocity, how fast you are moving, is equal to V over V naught times C minus C. And if you want it to factor, it is F over F naught C. Never mind. It would be factoring out the C. It would be F over F naught minus 1. Is factoring out the common factor of C. But either way, that is, so the new frequency is 500 hertz divided by 1,000 hertz times 343 meters per second minus 343 meters per second. We see that we are moving at negative 171.5 meters per second. Negative means you're moving away. So you're moving quite fast. Half the speed of sound. If you wanted to, what you could have done also is going back to this. VR is equal to F divided by F naught times C minus C. We could factor out the C like I was doing earlier. Minus 1 times C. This is going to be 500 divided by 1,000 minus 1 times C. And we see we get negative 0.5 C. So you're at half the speed of sound. You can leave it in terms of speed of sound to be more precise. By the way, this equation only works if you're less than the speed of sound. So you can't be, it only works if the relative motion is between negative C and positive C. So between negative 343 to positive 343. Once you start breaking the sound barrier, this equation no longer holds as we get overlapped. That's called a sonic boom, by the way. Let me load up the PowerPoint. Did the PowerPoint talk about Doppler effect at the end? Like the last thing it talked about. So Doppler effect also applies to light, increase in light frequency, when it approaches you, decrease. You can actually determine a star's spin, how fast it's spinning, by the Doppler effect. Part of it's when it's rotating, part of it's going to be moving away from you, part of it's going to be moving towards you. So you can figure out what the base color should be, and then you can figure out what color is on the right side and what color is on the left side, and actually calculate how fast a star is rotating. Blue shift, usually we all refer to this as redshift. It's just negative redshift or positive redshift. Redshift refers to something moving away from you. We know the universe is expanding. It's expanding at an accelerated rate. It's getting faster and faster and faster as it accelerates away from us. All the galaxies outside of our local cluster of galaxies are moving away from us, meaning that the entire space-time is expanding or stretching out. We know this because everything appears redshifted. We know what colors stars should burn at. But they all have different colors from what we expect because they're being redshifted. Doppler effect occurs for all types of waves, not just sound and light. So, wave barrier, waves superimpose directly on top of each other, producing a wall. This is whenever you approach the when you approach the sound barrier, when you approach the speed of sound, all these waves bunch up on each other. And what is a sound wave? It's a compression and a rarefaction. So if all the crests are hitting at each other, or getting closer and closer and closer, that means all the compressions are getting bigger and bigger and bigger. You're actually making almost a wall of air in front of you. Is why it's extremely difficult to actually pass the sound barrier. Once you do pass it, it's known as going supersonic. And you can actually measure based off of this angle how fast something is moving past the speed of sound based on the angle. We usually think of this as triangle, but it is in 3 dimensions. It's more of a cone. But we can see some object moving less than the speed of sound, then an object moving at exactly the speed of sound creates that barrier, and then right when it transcends going supersonic. And remember that wave has a compression and a rarefaction, so there's an area of high pressure and an area of low pressure. If something is going supersonic past these windows, most likely all the windows would break because of the sheer difference in pressures. This is known as a sonic boom. Actually, have you ever done a towel or a bullwhip, specifically a bullwhip, and popped it? It makes a really loud pop. Have you ever took a towel and then done it like that, and at the very end of it makes a loud popping noise? What is that pop? Well, have you ever done it in air? Have you ever missed? And did it make a loud pop? That is actually the tip of it breaking the sound barrier. The very tip of it is moving at greater than 343 meters per second. That's the crack of a whip sound, a supersonic bullet. Actually, have you ever heard of silencers and suppressors? So that loud popping noise, most of the sound bullet isn't from the explosion of the gunpowder. It's actually from the bullet creating sonic booms as it moves through air.
Isn't the sonic things like all them the air that affects?
Yeah, it prevents the air from escaping at greater than the speed of sound, which would thus create a sonic boom. And so what it does is slow down the air and make them release more slowly. So it removes the sonic boom from the escaping hot gas. But the bullet, if the bullet is still moving greater than the speed of sound, it would not muffle the sound hardly at all. Yes, the explosion from the gunpowder is gone, but the bullet is still making sonic booms. I think it was Smarter Every Day. Do y'all know what the slurring effect is? Do y'all know what the slurring effect is? Jeez, y'all don't know anything. It's if you take a camera and a point source, so a single point like one LED, and you shine a parabolic or a spherical mirror. Technically, I think it needs to be parabolic, but sphere is close enough. And it's going to reflect some light back. This technique allows you to see small differences in air. And basically, it allows you to visualize air molecules. So we have a camera here. You can see the small changes in air motion. It's very sensitive to air motion. That is a sonic boom, and the moment a bullwhip cracks.
What's up? I'm Destin. This is Smarter Every Day. This is the tip of a bullwhip, and that crack you hear is this breaking the sound barrier. My question is why, or how? Like, if you think about it, your arm's never leaving your body, and something's going faster than the speed of sound in just a few hundred milliseconds and over
This one?
Yeah.
several feet. That's a big deal.
Okay, now would be an excellent time for me to explain April. April Choi. So, April is an engineer first and foremost. I think all this whip business is just a reason for you to explore
Fluid dynamics?
Fluid dynamics. I really do. So April on the internet, you may have seen her Guinness Book of World Records whip stuff. She's good with whips. But what's really interesting about April is your brain.
There's something in fluid dynamics known as the no-slip boundary condition. That means air molecules that are right next to this fluffy part stay next to that fluffy part.
And so it's pulling that air with it.
It depends whether or not you're using a Lagrangian framework, which centers on here, or a Eulerian framework that centers on the overall mesh.
That's what I was thinking. I was wondering if it was a Lagrangian or Eulerian framework, but I wasn't going to say anything.
The first thing we did is create a new tip for the bullwhip and attach it to the whip, and then after that we set up the camera system.
The way we're getting this shot is using the Schlieren technique, and this is what took us so long to coordinate. Basically, we have a point light source right here, and that light is coming out, it's spreading out, it's hitting this mirror, this parabolic mirror, and as it comes back, what it's doing is it's converging to this point right here. You can see there's the light coming through at the focal point, and then we've got red and green gels right there, and then that's scary. Go watch Derek's video on Schlieren. It's better than this one. We're just gonna show you how a whip breaks the sound barrier. That is unnerving.
After everything was set up, we literally got cracking.
How she does not hit that mirror is amazing.
Okay, I triggered.
I guess that's why she's
We learned
overall.
two major things in my buddy's garage. First, a question though. At what point in the whip extension do you think the crack happens? So growing up, I used to play Castlevania a lot. And so for me, it made sense that the crack of the whip would happen at full extension of the whip, because that's what you want to do with the bad guys, right? You want to keep them as far away from you as possible. When we set up the high-speed camera expecting the whip to crack like it does in Castlevania, the shockwave would always enter the field of view before the whip did. Therefore, it was clear that the crack was happening before the whip was fully extended.
So it's cracking way back there.
It's cracking before we think.
I learned something. I didn't know that.
I didn't know that either.
It actually happens as the whip unrolls, not at the end like I thought. And in order to visualize what's happening, we switched from the overhand strike to the sidearm strike. What you're about to see here are two engineers that have researched this stuff, and we're totally blown away because the experiment worked, and we're starting to see things for the first time that we totally didn't expect.
Okay, we are getting somewhere.
And based on this angle, that angle it makes, you can actually calculate how fast just by the degrees. You can look up the formula if you want to.
The second thing we learned in the garage is there may be a mechanism that's causing it to accelerate just before breaking the sound barrier.
Those strands right there are not in tension. Do you see that?
Yeah, it's chaos.
And then there's this moment
They all come together.
where they all come together, and when it starts to pull, that's when the initial shock wave starts.
So when it's the collapse.
The collapse is when it happens.
And the drag coefficient is going down.
The fact that we're seeing a new mechanism,
They hook her up to light reflectors. These things reflect a lot of light, and they have cameras around the room. So these cameras are taking a lot of shots that has reflective tape on it.
watching is 5,000 frames per second. You can see that the Vicon cameras up on the wall are taking data at 500 hertz, which means they're flashing every 10 frames on the high-speed camera here. You'll notice that the whip unrolls normally, very similar to how the paper from the University of Arizona described it mathematically. Let's make a few observations here. First, there seems to be a wave that moves down the whip. As the hand moves forward and then stops, it transfers momentum into the whip itself. Then one segment of the whip, as it unrolls and straightens out, seems...
So, mass times velocity, momentum is conserved. So what happens if the mass is reduced? The velocity goes up. So so initially the whole thing's moving together, but this back part of the whip is stopped. Where does the momentum go? The momentum has to go into the rest of the whip. So as she's holding onto this and stopping the back part of the whip from moving, the rest of the momentum has to be transferred into the rest of the whip.
transfer all of its momentum into the next segment, and then the next segment, and so on and so forth. As indicated by this red line moving along the bottom here, you can see the velocity of that straightening out of the whip moves forward. We can then look at the Atom Lab data and measure the input momentum in 3 dimensions and use that information as a tool to help us build a model.
So the whip's coming up towards the mirror.
Yeah.
That's awesome. Is that awesome?
Yes.
Another thing to look at is what's happening on the top of the whip. The velocity is speeding up. Most researchers think this has to do with the conservation of momentum. The whip is tapered, so each smaller section on the way down has to speed up to maintain the same amount of momentum. This is the exact reason we took so much time up front to measure the mass and dimensional properties of the whip all the way.
So anytime you hear a loud crack, most likely what's happening is something is breaking the sound barrier like that. Let me see. I'm going to redo the homework. I was going to pass it out today, but I need to expand on it. Yes? You won't? Alright. Are you going to still be in chemistry?
Yeah.
But, next week, I'm going to move away from this and go into reflection and other things. This is quite simple. It's just use the formula and play around with it. The other stuff's more advanced.